Assalamu alaikum everyone. I hope you're all doing great. I welcome you all to the third lecture on analog and digital electronic circuits, in which we will study the use of BJT in the design of amplifier circuits. Although I'm sure that you must have studied bipolar junction transistors in one of your previous courses, uh, nevertheless, I will give a brief introduction. In particular, I will go through the two important modes of operation of the transistor, namely the active mode, forward active mode, and the saturation mode of operation. I will also discuss their current and voltage characteristics. After that, we will use the bipolar junction transistor to construct a voltage amplifier. In particular, we will look at the need for biasing of the transistor for its use as an amplifier. And we will study the effects of non-linearities of the transistor on the output of the voltage amplifier. So bipolar junction transistor, abbreviated as BJT, is a three-terminal semiconductor device. The three terminals are called collector, base, and emitter, represented by C, B, and E, respectively. BJTs come in two flavors, namely the NPN BJT and the PNP BJT. An NPN bipolar junction transistor has collector and emitter regions made up of N-type semiconductor materials, and base region is made up of P-type semiconductor material. Whereas a PNP BJT has collector and emitter regions made up of P-type semiconductor materials, and the base region is made up of N-type semiconductor material. Base region is always sandwiched between the collector and emitter regions. So these are the symbols used to represent NPN and PNP bipolar junction transistors. The direction of the arrowhead shows the direction of the conventional current flowing through the emitter branch. So for an NPN BJT, the emitter current flows out of the emitter terminal into the external circuit. Whereas for a PNP BJT, the emitter current flows uh, into the emitter terminal from the external circuit. So I will focus on the use of NPN BJTs for the design and construction of amplifiers. PNP amplifiers can be readily obtained from the NPN amplifiers by reversing the polarities of the voltages and the directions of the branch currents. So BJT is constructed using two PN junctions, namely the emitter-based junction and the collector-based junction. And since each PN junction can be biased in either it can be biased as in the forward mode or in the reverse mode, this gives a total of four modes of operation for the BJT. When the emitter-based junction is reverse biased and the collector-based junction is reverse biased, the BJT is said to be in the cutoff mode. When the emitter-based junction is reverse biased and the collector-based junction is forward biased, the BJT is said to be operating in the reverse mode. When the emitter-based junction is forward biased and the collector-based junction is forward biased, the BJT operates in the saturation mode. And when the emitter-based junction is forward biased and collector-based junction is reverse biased, the BJT is said to be operating in forward active mode. In the context of amplifiers, we will be mostly concerned with the forward active mode of operation. However, as we'll see later, under some conditions, the BJT can be forced to operate in either saturation or cutoff mode as well. There is nothing much to say about the operation of BJT in the cutoff mode, except the fact that there is no conduction of current in the cutoff mode, which is why I will discuss the forward active mode and the saturation mode of operation. So in the forward active mode of operation, emitter-based junction of the BJT is forward biased and collector-based junction is reverse biased. And as a result, the electrons are injected from the emitter region into the base region. And since there is a difference of concentration of electrons at the boundaries of the emitter base and collector base junctions within the base region,
these electrons are diffused towards the collector-base junction. As they reach the boundary of the collector-base junction, they are swept across the depletion region, and this results in an electronic current flowing from the emitter through the base into the collector, which in turn gives us a conventional current that flows from the collector through the base into the emitter and is given by this expression, in which Vt is given by this equation, where K is the Boltzmann constant, given by this value, T is the temperature, and Q is the electronic charge. Vt is called the thermal voltage, uh, which is about 26 millivolts at the room temperature of 25 degrees Celsius, whereas Is is called the saturation current or the scale current, which depends upon the device parameters. In particular, it is given by AE, which denotes the cross-sectional area of the emitter-base junction. Q is the magnitude of the electronic charge. Dn represents the diffusivity of electrons in the base region. W represents the effective width of the base region, that is the width of the base region, excluding the depletion region. Np naught is the thermal equilibrium value of the electron concentration within the base region, which is defined by the square of intrinsic carrier density in the base region and the doping concentration in the base region. The base current, the current flowing from the collector through the base into the emitter, results in the base current as well, which flows into the base terminal and is given by a fraction of the collector current as IC over beta, where beta is the transistor parameter. Furthermore, we get the emitter current as the sum of the base and the collector currents. So using this expression, we can represent this emitter current in terms of the collector current through this parameter alpha, which is defined in terms of beta. So alpha is always less than 1, in fact very close to 1, smaller than less than 1. We can invert this expression to represent the emitter current in terms of the base current through the transistor parameter beta. And this equation can be used to represent the emitter current in terms of the base emitter voltage, like this, 2 alpha. So using these expressions for the collector and emitter currents, we can construct a model for the bipolar junction transistor operating in the active mode. This model is called the T model because of its shape. And in this model, we represent the collector current as a voltage controlled current source because its value depends upon the voltage VBE. So we can represent it as a voltage controlled current source with value given by this expression. Since the base emitter or the emitter base junction is forward biased, it is represented with a forward biased diode. And using this expression for the emitter current, in which Is over alpha can be thought of as the scale current of the forward biased diode, we specify this diode with the scale current Is over alpha. So this emitter base junction is represented by a forward biased diode having forward biased voltage VBE and scale current Is over alpha, because IE depends upon the scale current Is over alpha. We can equivalently represent this T model by using, instead of voltage controlled current source, a current controlled current source, because as you've seen, IC can be written in terms of IE through alpha, so we can equivalently represent the collector current as a current controlled current source. These two models are perfectly equal. Furthermore, we can, if we consider in this model the base emitter terminals to be constituting an input port and the collector base terminals to constitute an output port with base terminal common between the input and output ports, then for the input current IE, for the current IE flowing through the input port, we get the current IC through the output port, which is given by alpha times IE. So alpha can be thought of as the um, current gain of the transistor in this configuration, in which base emitter terminals are considered as input port and the collector base terminals are considered as output port. So in this context, alpha is also called the common base current gain, because base terminal is common between the input and output ports, and for a current IE flowing through the input port, we get an output current as alpha times IE. So alpha is the common base current gain of, of the transistor. By manipulating the equations for the collector current and the base current, we can represent the collector current by shuffling this expression, and we can represent it in terms of base current as beta times IB. Similarly, since the emitter current is the sum of collector and base current, so base current can be written in terms of the emitter and collector current like this, where this expression follows from this expression, this equation. So using these set of equations, we can construct another model for the NPN BJT, which is called the pi model, in which again the collector current is represented by this voltage controlled current source according to this expression. And the base emitter junction, because the base emitter junction is again forward biased, it can be represented by a forward biased diode. But however, unlike in the P model where we put the diode in the emitter branch, in the pi model we put the diode in the base branch using this expression for the base current. Since the base current is given by saturation current divided by beta, so we assume that this diode representing the forward biased emitter base junction has a scale current of IS over beta, because it carries IB instead of IE. Previously, the forward current of the diode was modeled by IE, which was given by IS over alpha. However, in this case, since the forward bias diode has been put in the base branch, the current flowing through the forward bias diode, which is defined by the forward bias base emitter voltage, is IB, and IB specified by IS over beta. So we designate this diode with a scale current of IS over beta. And the directions of the currents are such that the emitter current is the sum of the base and collector currents, as before in the P model as well. The emitter current was the sum of base and collector current. So here as well, emitter current is the sum of collector and base current. So again, instead of using this expression, we can use the expression that relates the collector current with the base current through beta and represent the collector current instead of a voltage controlled current source. We can represent the collector current by a current controlled current source. So the collector current is now given by beta times IB. So these two models are again perfectly equivalent to each other. So again, if we assume that the base emitter junction is, if we assume the base and emitter terminals to constitute the input port and collector emitter terminals to constitute the output port, then we observe a current of IB flowing through the input port and a current flowing through the output port, which is given by beta times IB. So the output current in this context is amplified by is an amplified version of the input current ID, which is why beta is also called the common emitter current gain. It's called common emitter current gain because emitter is the common terminal between input and output ports. So just like alpha was called the common base current gain, beta is called the common emitter current gain. So when the collector-based junction is forward biased, while keeping the emitter-based junction forward biased, the transistor enters the saturation mode of operation. But we know from the theory of diodes that PN junction does not start conducting appreciably or does not become fully forward biased unless the forward voltage across it exceeds about 0.4 volts or so. So the transistor enters the saturation mode only when a collector-based junction becomes forward biased or the forward biased voltage across the collector-based junction exceeds 0.4 volts or so. So when that happens, the collector-based junction starts conducting appreciably in the forward mode, and hence we can augment the pi model with another forward biased diode, but in this case with a different scale current. Because the scale current depends on the cross-sectional area of the P end of the collector-based junction. So for the collector-based junction, scale current is directly proportional to the cross-sectional area of the collector-based junction. And since the collector-based junction has a much larger cross-sectional area than the emitter-based junction, this forward biased diode modeling the forward biased collector-based junction has been shown to have a different scale current than IS. IS was the scale current corresponding to the emitter-based junction, but IS subscript BC is the scale current corresponding to the collector-based junction because collector-based junction has significantly larger area than emitter-based junction. So IS-BC will be larger than IS. So writing the current equation at this node, we can very easily see that the collector current now is given by the difference between the current through this branch and the current conducted by the forward biased collector-based junction, which is given by this term. So as the forward biased voltage across the collector-based junction increases, this term increases, which decreases the collector current. So when the transistor is operating in the saturation mode, its collector current is reduced. Similarly, by writing a current equation at this node, we can very easily see that the base current is the sum of the current conducted by the forward biased base emitter junction plus the current conducted by the forward biased collector base junction, given by these two terms. So this is the current conducted by the forward biased diode modeling the forward biased emitter base junction. This is the current conducted by the forward biased diode modeling the forward biased collector base junction. So this depends on the base emitter voltage and this depends on the base collector voltage. So for a transistor operating in saturation mode, not only its collector current is reduced, but its base current is increased, which means that the ratio of collector to base current is reduced. And this ratio is now called beta forced. It is called beta forced because we can set any value of the collector current as well as the base current by choosing an appropriate value of the base collector voltage. And hence this ratio can be set to any value by choosing by adjusting the base collector voltage or the collector base voltage, which is why this is called this ratio is called the forced beta now. And obviously, because IC decreases, ID increases in saturation, so this ratio is less than the beta of the transistor, which was the ratio of the collector to base current in the forward active mode. So furthermore, if we look at this augmented pi model and write an equation for the voltage around this outer loop, then we can find that the collector emitter voltage is given by the difference between the base emitter voltage and the base collector voltage. Now, since the collector-based junction has a much larger junction area than the base emitter junction, from the physics of diode, we know that the collector-based junction will start conducting appreciably at smaller uh, forward bias voltages, which is why the base collector forward bias voltage will always be smaller than the base emitter forward bias voltage by about 0.1 to 0.3 volts. And so the saturation, the collector emitter voltage, while the transistor is operating in the saturation mode, is given to be in this range, about 0.1 to 0.3 volts. We also note that since these voltages VBC and VBE, they are the forward bias diode voltages. From the first order model of the diode, we know that the forward bias voltage is almost constant. It varies very slowly. So for the forward bias diode representing this forward bias collector base junction, as well as the forward bias diode representing the forward bias base emitter junction, their forward bias voltages, they vary very slowly with current. It is the current that varies a lot, and the voltage almost remains constant, which means that their difference will almost remain constant. Which is why we have chosen to represent the collector emitter voltage in saturation mode of the transistor as a DC quantity. So if you remember the convention, we represent DC voltages with uppercase letters and uppercase subscripts. So the subscript here is CE. Sat simply indicates that it is the collector emitter voltage in the saturation mode. So this represents a DC quantity only because this varies very slowly. This decreases very slowly. As the transistor goes deeper into saturation, VBC increases and VCE sat decreases, but it does so very slowly because VBC increases very slowly. VBE also increases very slowly because the forward bias voltage is almost remain constant, and VCE sat decreases very slowly. So we denote it with a DC quantity, VCE sat. We also note that since collector current decreases with increase in VBC, there will be a voltage VBC at which this term equals this term. At that point, collector current will become 0. So when the current through the forward bias collector base junction equals the current through the forward bias emitter base junction, the collector current goes to 0, and this happens at the collector to emitter voltage, which is given by this expression. So we refer to the collector to emitter voltage at which IC goes to 0 as VCE, 0, and it is given by this expression, which can be readily obtained by solving this equation and realizing that VCE is actually given by the difference of VBE and VBC to this relation. So here I show the collector current versus collector emitter voltage characteristics. So collector emitter voltage is shown on the is given on the x-axis. Collector current is given on the y-axis, and these curves have been plotted for a transistor having saturation current IF equal to 10 to the minus 14 and saturation current IFDC equal to 10 to the minus 12 amperes at a temperature at which the thermal voltage is equal to 26 millivolts. Furthermore, we have assumed that the saturation voltage, the collector emitter voltage in the saturation mode of the device is about 0.3 volts. And these curves, these IC versus VCE curves have been plotted for different values of the base emitter voltage. So for example, this blue curve corresponds to a base emitter voltage of 0.54 volts. The red curve corresponds to a base emitter voltage of 0.56 volts. The yellow curve corresponds to 0.58 volts, zero point 0.6 volts, 0.60 volts, and 0.64 volts. This dotted line for each curve shows the edge of saturation or the edge of reactive mode. So this dotted line is actually a vertical line plotted at VCE is equal to 0.3 volts or so. So when VCE drops below 0.3 volts, the transistor enters the saturation mode. For VCE greater than 0.3 volts, the transistor is assumed to be operating in reactive mode. So in reactive mode, the transistor current is dependent on VBE only. It is given by an exponential dependence on VBE and has no dependence on VCE. That is why these curves have been shown as horizontal curves in the active region of operation. There is no dependence of IC on VCE in the active mode. However, IC drops to 0 for diffusing VCE in the saturation mode. Please note that later on we will actually find that there is some dependence of IC on VCE, which is given by the early effect, but this early effect has been ignored in this diagram, which is why IC is just a constant against VCE, no dependence on VCE in the active. This figure shows the plot of the collector current versus the base emitter voltage, which is related to the base emitter voltage again through this relation, which is shown here for ease of reference. So as can be seen, IC depends exponentially on VBE. So as soon as VBE becomes sufficiently large, IC grows exponentially. Hence, these characteristics, IC versus VBE characteristics, are extremely nonlinear because of the exponential dependence of IC on VBE. And these characteristics have been shown for an NPN BJT having scale current equal to 10 to the minus 14 amperes at such a temperature at which VT is equal to 26 millivolts. So IS is a highly temperature dependent quantity, which is why I always specify it at some temperature or equivalently at some thermal voltage, because thermal voltage has one-to-one correspondence with the temperature. So I can either specify IS at a temperature or at the corresponding VT. So speaking of the temperature dependence of IS, we find that IC depends on temperature through not only just VT but also through IS, because IS is proportional to Ni squared, the intrinsic carrier density, and the intrinsic carrier density in turn is given by this expression, in which B is a material dependent parameter, which has value equal to this for silicon. T is the temperature, K is the Boltzmann constant, and Eg is the band gap energy, which for silicon is about 1.12 electron volts. Or you can represent it in terms of joules by realizing that 1 electron volt is equal to 1.602 into 10 raised to the power minus 19 joules. So since Ni is a strong function of temperature, it makes IS a very strong function of temperature. So IC is dependent on temperature through VT and IS. So in this diagram, I show the IC-VBE characteristics at different temperatures. So this blue curve shows the characteristics at 298 Kelvin. The red curve shows the characteristics at 308 Kelvin, and this yellowish orange curve shows the characteristics at 318 Kelvin. For a transistor having the scale current equal to 10 to the minus 14 amperes at VT 26 millivolts. So as can be seen that let's see, when we increase the temperature, the IC-VBE characteristics move towards the left. in this direction. Or in other words, if we keep IC constant, then increasing the temperature decreases VBE. That is why the characteristics, IC VBE characteristics are shifted in this direction. So VBE at a constant IC, VBE decreases with increasing temperature. And we can quantify this decrease by finding VBE at T1, T2, and T3, and then taking the difference between VBE at T1 and T2 and dividing it by the difference in temperature. So basically this blue and red curves, which are almost overlapping, they represent the change in VBE versus temperature per unit temperature. So T1 is 298 kelvins, T2 is 308 kelvins, and T3 is 318 kelvins. So the blue curve, for example, shows that the change in VBE due to temperature per unit temperature is about 1.6 to 1.75 volts, millivolts per degree C. And similarly, this orange curve shows that the change in VBE per unit temperature is again the same, about 1.6 to 1.7 millivolts per degree C. So in your textbook, it has been stated that VBE changes by minus 2 millivolts for every 1 degree C rise in temperature. So this is very close to minus 2 millivolts per degree C. But these curves show a decrease in VBE of about 1.6 or 1.7 millivolts per degree C. So that is very close to the given value of minus 2 millivolts per degree C. So in the textbook, minus 2 millivolts per degree C means that VBE decreases with increasing voltage. So here again, these curves show the decrease in VBE because T1 is smaller than T2. So as T1 is changed from T1 to T2, so T1 is smaller than T2. So as temperature is changed from T1 to T2, these positive values show that VBE has larger values at T1 than at T2. So increasing the temperature from T1 to T2 results in a positive difference of VBE, which means that VBE decreases as we change the temperature from T1 to T2 by about 1.6 to 1.7 millivolts per degree C. So from the pi and T models, let me go back to the slide representing pi and T model. So let's look at T model. So for this T model, if I assume that the emitter base terminals form an input port and collector base terminals form an output port, then for the input voltage of VBE, I get an output current which is defined by VBE. I get the output current IC, which is defined by VBE. So this model represents the BJT as a transconductance amplifier, generating output current based on input voltage. Similarly, this model as well, if I consider the base emitter terminals as the input port and collector emitter terminals as the output port, then based on the input voltage, I get an output current IC. So IC is defined by the input voltage. So again, this model defines BJT as a transconductance amplifier, giving output current based on the input voltage. Equivalently, we can consider this model in which, again, if this is the input port and this is the output port, then corresponding to an input current IE, we have an output current IC, which is alpha times IE, where alpha is the gain. So the output current is defined by the input current. Hence, according to this model, BJT can be represented as a current amplifier. Similarly, in this equivalent pi model, if again I consider C the collector emitter terminals as the output port and base emitter terminals as the input port. Then corresponding to the base current IB, I get a collector current, I get an output current IC, which is defined by the base current. So corresponding to IB, I get an amplified IC given by beta times IB. So this equivalent pi model also represents the transistor BJT as a current amplifier. So depending upon what model we use, we can consider BJT as either a transconductance amplifier, generating collector current at the output corresponding to base emitter voltage at the input, or we can consider BJT as a current amplifier, generating collector current at the output corresponding to emitter or base current at the input. So this indicates that since pi and t models represent the operation of the transistor in the active mode, so this indicates that BJT should be operated in active mode if it is to be used as an amplifier. And the resulting transconductance or the current gain of the BJT can be converted into the voltage gain through this circuit by connecting a resistance RC with the collector terminal. So in this circuit, we consider the collector emitter terminals as the output port and base emitter terminals as the input port, with emitter terminal as common. That is why this is called a common emitter configuration. On the input, we have a signal, the input signal VBE, which produces an output current IC, which passes through the resistance RC, and the whole circuit is powered by the DC source VCC. And in this circuit, we label the output voltage as VCE. So VCE is the output voltage. So again, considering this loop and writing the voltage equation, we can very easily find the output voltage VCE to be given by VCC minus the drop across RC, minus this drop across RC. So since IC is related to the input voltage through this exponential dependence, we get VCE as VCT minus this term. And this expression is called the load line of this voltage amplifier. This is called a voltage amplifier because small changes in the input voltage are exponentially mapped into the output voltage. So for small input voltage, we get a large output voltage through this load line. And this load line basically gives the operating point of the circuit, because the operating voltage VCE will always satisfy this equation. So the load line will always give the operating point of the circuit. Please note this negative sign in the load line. Because of this negative sign, the output voltage will be completely out of phase with respect to the input voltage. So when the input voltage is increasing in the positive direction, the output voltage will be decreasing in the negative direction, and vice versa. Which is why this voltage amplifier configuration is also called the inverting configuration, because the output is an inverted version of the inverted amplified version of the input. So here I show the load line of the voltage amplifier superimposed on the IC VCE characteristics. So the load line has been obtained for a VCC of 5 volts and a collector resistance of 10 kilo ohms. Slope of the load line from this equation can be seen to be equal to 1 over RC, which means that increasing RC will decrease the slope of the line, and decreasing RC will increase the slope of the line. So as before, this dotted black line shows the edge of saturation, assuming VCE sat is equal to 0.3 volts. So as mentioned before, the operating voltages and currents of the voltage amplifier, they will always lie on this load line. So when IC is 0, when VCE becomes equal to VCC, that is this point here. At this point, IC is 0 and the output voltage VCE is equal to VCC. Similarly, when VCE is 0, IC is equal to VCC over RC. So that is this point. So at VCE 0, IC is equal to VCC over RC. So the operational voltages and currents, they will always be on this line between these two extremes. However, as noted before, in order to use BJT as an amplifier, it must be operated in active mode, active region of operation. So the region of operation on the curves towards the right of this dotted line is the active region of operation. So if we mark the intersection of the load line with this dotted line at which below which with respect to VCE the transistor enters the saturation mode, then this point A refers to the edge of saturation, meaning that for operating voltages and currents lying on this region of the on this portion of the curve, the transistor will be operating in saturation mode. Similarly, considering the intersection of this load line with this blue curve designated by VDE1, so this is the IC-VCE curve when the base emitter voltage is equal to VDE1. So considering that for base emitter voltage is less than VDE1, the device enters saturation. For example, VDE1 could be equal to 0.4 volts, and below 0.4 volts, the emitter base junction is essentially reverse biased and there is no conduction. So considering that the device turns on at VDE1, then for operational voltages lying within this portion of the load line, we consider the device to be operating in the cutoff mode. So for voltages which lie on this portion of the load line, which corresponds to a region of the IC-VCE curves for which VDE is less than VDE1, and we assume that VDE1 is the minimum voltage required to turn the transistor base emitter junction on. Such voltages will drive the transistor, such operating conditions will drive the transistor into the cutoff mode. So these operating conditions will take the transistor into saturation, and these operating conditions have been assumed to be taking the transistor into the cutoff mode. So the points A and B, they mark the edge of saturation and cutoff, or the edge of the active mode at these two extremes. So for BJT to be used as an amplifier, the operating voltages must be such that they lie within the portion of the portion of the load line between points A and B. So in order to ensure that the amplifier or the BJT operates in the active mode, or in other words, in order to ensure that the operating voltages lie between points A and B, we must apply appropriate DC voltages to the amplifier. And application of appropriate DC voltages to ensure the operation of the transistor in the active mode is called the biasing of the transistor, which is shown in this circuit diagram here. So in this circuit diagram, we have actually decomposed the overall signal into two parts. So if you notice, we show the overall input signal as a mixed signal. So this is represented by a lowercase letter with an uppercase subscript. So this is a mixed signal. It can have AC plus DC both. But here we have separated the AC voltage out from the DC voltage. So this is our signal which we intend to amplify, and this DC voltage is applied with the sole purpose of biasing the BJT so that it operates within this portion of the load line, that is within the active mode, within the active region of the characteristic. So the only reason we applied this VBE is to make sure that the transistor operates in the active mode. The corresponding output voltage, the output voltage VCE, which corresponds to both the signal and the DC input supply, is given again by a mixed signal VCE, and the DC content of this VCE, which corresponds to the DC input voltage, along with the DC content of this output collector current, which again corresponds to the DC input voltage. These two DC values are called the bias point of the amplifier. The bias point of the amplifier is also called quiescent point or Q point because it contains zero signal component. The DC components of IC and VCE, they have no contribution from the signal. That is why they're also called quiescent point or Q point, or they're also called operating points. So there are different names for the same quantity: bias point, operating point, Q point, quiescent point. It all refers, all of these terms, they refer to the DC content of the output current and voltage corresponding to the DC biasing voltage at the input. So the bias point is given by this set of equations. So if you want to find out the contribution at the output because of this source, we kill this AC source, that is we short circuit the AC source, and then we'll be only left with VBE as the base. So killing this AC source gives VBE as the base emitter voltage, and corresponding to the VBE, we get the collector current IC, which is given by this relation. This is a DC quantity because it represents contribution from the DC biasing voltage. Similarly, we get the VCE, the DC component of the output voltage VCE, which is given by VCC minus ICRC. So it is again represented as a DC quantity because it is given by the DC biasing voltage as VCC minus ICRC. So this is called the bias point. The combination of DC output current and DC output voltage is called the bias point of the circuit. Since the total base emitter voltage is the DC biasing voltage plus the signal, we write again for ease of reference the total output voltage, which is given by the total input voltage through this relation. And since this expression relates the total output voltage with the total input voltage, it represents the voltage transfer characteristics of the amplifier. So if you remember from the first lecture, I think we defined the voltage transfer characteristics as the equation that relates the output voltage with the input voltage. So this is exactly that. It relates the output voltage with the input voltage and hence defines the voltage transfer characteristics. So we can plot VCE versus VBE, and it looks something like this. So again, this voltage plot or the voltage transfer characteristics have been plotted for a BJT having scale current equal to 10 to the power minus 14 amperes at this temperature, at a temperature corresponding to a thermal voltage of 26 millivolts. VCC has been set to 5 volts because we require VCC as well. So VCC has been set to 5 volts in this circuit, and RC is given by 3.5 kilo ohms. So as can be seen in these characteristics, when VBE is less than about 0.4 volts or so, the transistor is in cutoff mode because the emitter-base junction is essentially reverse bias. When there is no current through the transistor, this term is 0, which means that output voltage is equal to VCC, a constant. So the output voltage here is equal to VCC. As the as the base emitter junction voltage is increased, the emitter base junction becomes forward bias, and the transistor starts to conduct in the active mode, and we get this large slope. So for small increase in VBE, we get a large decrease in VCE, according to this equation. Because for a small increase in VBE, we get a large increase in this term, and we get a large decrease in VCE because this term is subtracted from VCC. So we get a large decrease in VCE corresponding to small increase in VBE. So this large slope is actually indicative of the voltage gain. That is, we get a large output, we get a large change in the output voltage corresponding to small change in the input voltage. So the ratio of the slope of this curve, actually, the ratio of delta VCE to delta VBE, which is the slope of this curve, is actually the gain, the voltage gain of this amplifier. And as VBE is further increased, VCE is decreased to a point at which it becomes equal to about 0.3 volts or so. When that happens, the device enters the saturation mode, as discussed before. And for simplicity, in this diagram, I have assumed the collector emitter saturation voltage to be constant, equal to 0.3 volts. You know that it varies very slowly, but I have assumed to be a constant, equal to about 0.3 volts or so. So this refers to this part of the characteristic corresponds to the cutoff mode of operation of the transistor. This part of the characteristics corresponds to the saturation mode of operation of the transistor. And this part of the characteristics between these two dotted lines corresponds to the active mode of operation of BJT. So here I graphically show the voltage gain of the amplifier. So I bias the transistor at 0.65 volts. So the overall input voltage is given by 0.65 plus this AC signal. So this AC signal is the signal that we intend to amplify. It has a frequency of 50 hertz and is given by a peak amplitude of 10 millivolts. So it is shown here. So this dotted line shows the DC component of VBE, and this signal is riding over the DC component here like this. So this is the composite signal VBE, having 0.65 volts as the DC offset and a 0.01 volt peak sinusoidal waveform riding over the DC offset. The corresponding DC voltage in the output, which corresponds to this DC voltage at the input, is about 2.5 volts. So this dotted line shows the DC component of the output voltage. And this sinusoidal waveform shows the output because of this sinusoidal waveform at the input. So basically, this output along with this DC voltage is the result of this equation. In which this is the response due to the AC component in the input, and this dotted line is the response because of the DC component, this dotted line DC component in the input. So in this case, VCC is still set to 5 volts, but and RC is given by 3.5 kilo ohms. So we can see that for a small input voltage, we get a large output voltage, which is completely out of phase with respect to the input. As the input rises in the positive direction, the output goes down in the negative direction. So it's because of the inverting nature of the amplifier. So we get an amplified version of the input voltage at the output voltage at the output. So in this slide, I show the effect of the collector resistance on the bias point of the amplifier. So for convenience, I have repeated this expression of the output DC voltage corresponding to the input DC voltage. And as can be seen that increasing RC increases this term, which in turn decreases VCE. So the Q point moves down the VTC because the DC value of the output voltage is reduced now. So previously, when we biased the amplifier at a output DC of 2.4 volts, now in this case, increasing RC from 3.5 to 5 kilo ohms biases the transistor at 1.4 volts. So the Q point has been decreased, has been moved down the VTC. The output DC voltage has been reduced, which does not leave a lot of room for the voltage, for the output voltage tail swing, meaning that as the output voltage swings in the negative direction, then for some instantaneous values of the output voltage, the transistor enters the saturation mode. And in the saturation mode, as has been assumed for simplicity, there is no gain, absolutely whatsoever. There is zero gain. For any change in the input voltage, there is no change in the output voltage. The output voltage remains constant. This is what we have assumed for simplicity. So as soon as the transistor enters the saturation mode, the gain becomes, the voltage gain becomes zero. And the output voltage becomes constant, equal to about 0.3 volts. So this is observed as the clipping of the negative peak of the output voltage. So we say that increasing RC does not leave a lot of room for voltage tail swing. The tail of the or the negative part of the output voltage does not have enough room to swing fully to its peak value. It is clipped at about 0.3 volts or so. So similarly, instead of increasing RC, if we decrease RC, then this term decreases and the overall difference increases. So VCE, the DC component of the output voltage, it increases, which shifts the Q point up the voltage transfer characteristic. So for example, in this case, we have decreased RC to about 100 ohms. From 3.5 kilo ohms, we have decreased RC to about 200 ohms, which has increased the output DC voltage to 4.93 volts, almost making it equal to 5 volts. So this does not leave a lot of room for the voltage head swing, meaning that as the voltage in the positive direction at the output increases, it quickly becomes equal to VCC, because the output instantaneous value of the output voltage cannot be greater than VCC. It quickly becomes equal to VCC because it is already biased at 4.93 volts. So as it rides 4.93 volts, there is only 0.07 volts left for the positive swing of the output voltage. So it quickly becomes equal to VCC, and then when it becomes equal to VCC, the transistor enters the cutoff mode. When the transistor enters the cutoff mode, again, the gain becomes zero because the output voltage becomes constant. For any change in the input voltage, the output voltage becomes constant. So this effect is manifested in as the clipping of the positive peak of the output voltage. So please note that previously we kept the input voltage to about so previously we used an input voltage which had a peak value of the AC component of which had a peak value of 10 millivolts. Now we have increased the input AC voltage so that now it has a value of about peak value of about 100 millivolts, of exactly 100 millivolts actually. So we have increased the input voltage And the reason behind this is to uh, visually show the effect of slipping on the output voltage. So we increase this input voltage in order to show the slipping of the output voltage uh, at the positive side, slipping of the positive piece of the output. So to conclude, the transistor must be operated in active mode for its use as an amplifier. As soon as the transistor enters the saturation or the cutoff mode, the gain is drastically reduced, and this reduction in gain manifests itself as either the clipping of the positive peak or the negative peak. So in order to avoid this, the amplifier or the transistor should be biased in the middle of the active region of the voltage transfer circuit, just like we did here. So if we bias the transistor in the middle of the active region, then we give the output voltage a chance to fully swing in both directions before forcing the transistor into either saturation or in the cutoff mode. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.